Hello and welcome to our final presentation for Chem 470. My name is Logan Renninger, and I'm joined here today by my teammates Brendan Jenkins, CJ Stiles, and Matt Jaeger. We are all senior chemical engineering students at Penn State University, and today's presentation is about a process that we designed to convert natural gas into methanol. The presentation today will be broken into the following elements. We'll start with background information about the site location and about specifications and constraints to our process. Next, we'll go into a process overview which walks through a block flow diagram and highlights key capital equipment and key design decisions for our process. After this, we'll go into an economic analysis which calculates our operating and fixed costs as well as our capacity and evaluates our profitability as a plant. After this, we will show you some sensitivity analyses that we conducted to evaluate how changes in market value and design decisions would affect the profitability of our plant. Lastly, we will finish with our final recommendations based on the results of these analyses and how to proceed. So our company, Nitlion Chemicals, has 3 locations, the first of which is a research and development R&D site at University Park, where we are doing our detail engineering. The second of which is a brownfield site in Houston, Texas, and the last is a brownfield site in Philadelphia, Pennsylvania. After careful consideration, it was determined that our site would be built in the Philadelphia site. Located on the Delaware River, the Philadelphia site offers rail and ship transport, as well as a lot of local talent to run the plants. Additionally, as you can see by this diagram, we are just miles away from the Marcellus Shale Formation, which offers readily available and cheap natural gas to feed to our process. Now I'd like to get into some of the constraints to our process. So we were given a feed stream of 19 million standard cubic feet per day of natural gas, which we can purchase at about 4 cents per pound. Once we put that through a process, we will be able to convert it into methanol, which we can sell at about 12.5 cents a pound. For one of the constraints for our process, we were expected to target a minimum mole conversion of methane in our feed to methanol as our product. We have 90%. So let's take a closer look at that feed stream and what it looks like. If we break it down, it's about 90% methane, which is our raw material that we need to convert into methanol. But additionally, there are 10% impurities, and there's a variety of impurities, which will need to be removed throughout the separation and purification processes. The feed stream is coming in about 80 degrees Fahrenheit, which is just slightly above ambient temperature, and 400 psi, so it's pressurized and has flow. So now my teammate Brandon Jenkins will go through how we convert this feed stream into methanol.
Hello, so as Logan said, we have to start removing some of the impurities from our feed stream. And the first impurities we're going to look at are those that will corrode our process units later downstream. So our first unit, as we can see above, is a desulfurization unit. And we bring in our natural gas feed and we pre-treat it in a multitude of heat exchangers so we can meet the separation conditions. So our first corrosive chemical is going to be here represented. It's hydrogen sulfide. Hydrogen sulfide is very corrosive to our process and can pose significant health threats to our employees if it leaks out of the system. Next, we're going to have mercury. Mercury again has some serious health problems and is also corrosive to our process. In addition to just corroding our equipment, the mercury can also kill our catalyst within our reactors. So as we can see, after going through the desulfurization unit, we have a purified methane stream and the waste stream coming out that is sent to a flare system to dispose of all the unwanted contaminants. So here we have a diagram of our actual factory setup where it's 2 parallel desulfurization units, and the idea behind this design was so that we have the entire feed flowing through one unit, and then once the catalyst is spent, we can divert all of the feed into the other unit while we either regenerate or replace the catalyst in the other feed. Speaking of the catalyst, it's worth noting that we're going to be using zinc oxide in this process. The zinc oxide will react with the H2S to form zinc sulfide. This zinc sulfide will then react with the mercury and pull it out of the process. At the end of the day, these units are going to be taking out 95% of our hydrogen sulfide and taking out 100% of our mercury. So now we've left our desulfurization units and we've disposed of our contaminants, and we've got this purified methane stream. This purified methane is going to be used to produce syngas in a steam reformer unit. So now that we have a steam reformer unit, we want to look at the chemistry involved. And so right now we can see where we convert methane and water to syngas, which is carbon monoxide and hydrogen. In addition, the carbon monoxide also reacts with water to produce CO2 and more hydrogen. So as we can see from these reactions, we need two things that aren't in our process yet. So we need to feed a water stream in, which we can see right here. We actually add a lot of medium pressure steam into our process to feed our reactions, and that is what will end up producing our syngas. Now what you also want to notice is that in our reactions we have heat added in. So here's a process diagram of what the actual unit will look like. We can see the steam coming in and the natural gas feed mixing together and then proceeding to move into the steam reformer unit. What this diagram hasn't mentioned yet is that our reactor goes at 1,140 degrees Fahrenheit at an operating pressure of 50 psia. In order to reach these extreme temperatures, we use two fired heaters. The first will preheat the feed stream into the reformer, and the second is going to maintain a constant temperature within our reformer by flowing exhaust gas as a jacket around our reformer to maintain constant temperature. So now we've converted our syngas, our methane stream to syngas. So the next logical step would be to turn this syngas into methanol. But being smart engineers, we know that we have a lot of energy coming out of this stream and we want to recover it and maintain it and use it where we can. So this syngas stream is actually going to be diverted and it's going to heat up our desulfurization natural gas feed that we saw previously and run through other parts of the process to provide energy to heat other streams. Now once we get back from this energy recovery efforts, we're going to go into a methanol synthesis reactor, as seen in the diagram now. So coming out of this methanol synthesis reactor, we're going to have crude methanol, which is going to be made up of a liquid and vapor phase. These are the primary reactions going on inside of our methanol synthesis reactor. In addition, we're not just creating methanol, we're also creating ethanol and methyl formate, which aren't listed above, but they are in trace amounts. So after we run through with a straightforward process, our conversion wasn't exactly where we needed to be. So in order to get to a better conversion, we added a recycle stream, which took out our gases and recycled them into the steam reformer. So now, this is a diagram of our actual steam or methanol synthesis unit. As we can see, it's running at 500 psia with a lot of pressure, and the temperature is down to 490 degrees Fahrenheit. Another unique feature of this reaction is that it's exothermic and actually produces energy that we can harness from the process. As we can see, as it follows, there's a flash drum which will actually separate our vapor from our liquid phase. So coming out of our flash drum and our liquid phase, we have a crude methanol product. The crude methanol needs to be converted to hit 99.85% purity during purification. In order to do this, we have a purification unit within our process. So what comes out of here ultimately is going to be a wastewater stream and then a methanol purity stream that we can sell. So here's a picture of our distillation columns. These are going to be used to purify our process, and ultimately this is how we're going to produce the methanol product we can sell. So the process design achieves target specifications at a capacity of 486 million pounds per year. Going into our specifications for this project, we need a conversion of 90% and a purity of 99.85% for methanol. After we look into our process, we can see that we get 97% conversion and we go to 99.87% purity, which meets our specifications and exceeds them. So now I'm going to hand it over to Logan again, and he's going to talk about the PDRI.
Thanks, Brandon. As part of our design methodology, we use a Project Definition Readiness Index, or PDRI for short, to monitor the definition of our project throughout its course. In the chart, you can see the PDRI scores for gate 3, 4, and 5 from left to right. The red line and green lines represent the maximum and minimum typical scores for each phase. As you can see, our scores fall nicely between these ranges, which puts us on a good course for our project development. Now, just like in golf, the lower your PDRI score, the better your score. So ideally, you want to minimize it. With a maximum of 1,000, you want to get it as low as you can. This red line here represents a PDRI score of 250. Generally, this is an accepted target to proceed to construction. So as you can see in our last gate, we achieved a PDRI score of 400, and while this is exhibiting a good sign of continued decrease, it is not yet at below that target. The reason we want to shoot for this target is that research has shown that projects with a PDRI score below 250 tend to be more successful in maintaining their schedule and budget. So these results would suggest that more time for developing a scope would be necessary. The reason that our scope is still undefined is that there is a number of items in the PDRI criteria that are not within the scope of our project. For example, detailed drawings for construction, electrical and wiring drawings, any permits, and most things related to construction and the physical building of the plant are outside the project for this class, since we are in preliminary engineering. So our recommendation would be that in order to achieve this score of 250, that more time to define the scope would be allowed and more time for engineering. And with that, we're going to get into our economic analysis with CJ.
So now I'm going to talk about the breakdown of the expense of our plant. So first I'm going to talk about the inner battery limits, or known as the IBO, capital equipment cost, which is right around $380 million. So the biggest area of this comes in the methanol synthesis. This is where we have 6 compressors and 6 heat exchangers, because we have to take the process feed from a low pressure into a high pressure to get better recovery of methanol. So the energy required for these compressors is fairly high, which causes the compressor size to be fairly high and give us a high capital cost. Next we go to steam reforming, which is the second biggest chunk here. And the reason the steam reforming is high is because it's an endothermic process, so it requires a lot of heat going into the stream. So the furnaces heating up the streams have a high capital cost since they are very large. So next we're going to talk about the outer battery limit, or known as the OBL, and this is around $84 million for a plant, so it's much smaller than the IBL. As you can see, it's broken down into utility, storage, environmental, and site development. So for the utility, this is just the fuel cost. This is basically just the fuel used to heat up the system. For the storage, this is for our product storage. For the environmental, we have to treat the water coming in, and we also have to treat the water going out of our plant to meet environmental specs. And then for the site development, this is just clearing out the site and stuff like that that involve this cost. So the overall total capital cost is around $720 million, and this is mostly due to the IBO, which is 50% of the cost. And like I said previously, this is due to the methanol synthesis and the steam reforming, where the compressors require a high capital cost, and also the furnaces used to heat up the streams and the steam reforming have a high capital cost too. Escalation is due to the inflation of the products or fuel that we're using, and this is basically based off the total capital cost. So next we're going to break down the utility costs. So utility wise, it costs 7 cents per pound of methanol produced. As you can see, the electricity is the highest part of our utility cost, and this goes back to the methanol synthesis. With the 6 compressors, they are energy intensive with electricity. So next we're going to look at the overall cost and how utilities play a role in operating the plant. So the plant is estimated to cost about 16 cents per pound of methanol to run. The taxes is based off of capital cost. So if we could figure out ways to lower our capital cost, we can figure out a way to lower our taxes, which would decrease the size of that chunk of our operating cost. So next, I'm going to pass it over to Matt.
Okay, I'm now going to talk to you about the economic evaluation of our process, beginning with the breakdown of the operating costs for producing our methanol. So it starts out, the raw materials cost us about 3.5 cents per pound of methanol we produce. We do have a slight gain in, we do have a slight source of revenue in the steam that we sell. We sell some small amount of high pressure steam and low pressure steam, and that gives us about 2.94 cents of revenue per pound of methanol produced. Next, we have our utilities at around 7.5%, or sorry, 7.5 cents. And finally, our fixed costs are about 8 cents per pound of methanol produced. The total of that is 16.09 cents per pound of methanol produced. This is a problem because our target sale price is 12.5 cents. This is going to result in a net loss for every pound of methanol that we produce. Considering that, we move on to the economic evaluation factors. So first of all, our after-tax rate of return is less than -30%. That is a significant loss of value. Speaking of value, our net present value for this project after its 15 years of operations is -$500 million. That value basically represents the economic loss that the company takes by building this project, and that is obviously quite significant. Finally, our required netback is the price that we would have to sell methanol at to achieve our desired rate of return of 15%, and that is 52.21 cents. That is a 418% markup from our desired sale price of 12.5 cents. What you see on the slide here is a graph of the cumulative cash flow. That is basically the revenue created by producing our methanol minus the capital costs and minus the operating costs. And as you can see, it caps out around -$550 million. That's a realistic plant, a well-designed plant would be in the positive around that value. And so this clearly represents an issue with our design. The next graph is our net present value. That is basically the sum of the cumulative cash flow. And again, this is negative. It caps out around -$490 million. That is, like I explained previously, that is the net loss that the company takes by building this project, and clearly it is quite significant. The next step in our economic analysis was to conduct some sensitivity studies. We wanted to see how economic factors and project variables would affect the overall profitability of the process when varied. So this first slide is changing the capital costs. We increase the capital costs by about 15%, and then we decrease them by about 15% to note the change in our economics. The graph you see shows the after-tax rate of return at varying methanol product prices. So at our target sale price of -12.5 cents, it's negative. We don't have a rate of return. It doesn't get positive until, or our required netback under these conditions, under the reduced capital costs, is around 46 cents per pound of methanol, which is better than the 52 of our base case, but still a considerable markup from our target sale price. The next sensitivity we studied was increasing the plant's lifespan. So normally this plant is designed to operate for 15 years, but by increasing this up to 20, we're able to increase the overall profitability of the process. Again, it's not profitable at base conditions at 12.5 cents, but it is better. Our required netback under these conditions is about 42 cents, which is better than even reducing the capital costs. Finally, our last analysis was what we called our best case scenario. We combined multiple of our sensitivity studies, including the capital cost reduction, the increased plant lifespan, as well as reducing the costs of our electric utility. And under these conditions, the plant is in a more realistic state. It's not Again, it's still not profitable, but it's better. It's at about negative 6.9% rate of return at our target sale price of 12.5%, and our required netback to achieve that 15% rate of return is only 36 cents, which is much better, still very far above our target sale price and even above projected methanol product prices. I'm going to now pass you off to Logan for our conclusions.
In conclusion, our PDRI analysis shows that further scope defining is needed to continue with our project. Our economic analysis suggests that our process is not profitable at its current conditions. Sensitivity analyses suggest that changing these conditions and changes in the market values for both cost and raw materials and price of methanol would not make this plant profitable. Therefore, with all these results in mind, is our recommendation that we do not build the plant at this time. If, however, there is a continued desire to build a methanol synthesis plant with this feed, significant design changes would need to be made to the process. This could happen in one of three main ways. The first of which would be to reduce capital costs, specifically in the methanol synthesis section. With our 6 compressors, that is a significant portion of our capital. By reducing the number of compressors, we could make the plant much more profitable. Second of which is to reduce our utility costs. Again, when we have less compressors, we would have less power costs associated with that section of the plant. Additionally, we could look at increasing more process-to-process heat exchangers to help with our heat values, and then again looking at possibly operating under less severe conditions to lower our utility costs, both for electricity and fuel to heat the process. The last and most simple of which is to simply further refine the process. The more ambiguity you have in your process, the more contingency you have to add in all of your capital estimates. So by simply further continuing our detailed engineering, we believe that we could lower the capital costs and therefore increase the profitability of the plant. So this concludes our presentation. We hope you enjoyed it, and thank you for tuning in.
As you can see in the background, we have some beautiful mountains. See, if you're getting tired of Chem E,
those are the mountains of Philadelphia,
you can just go up here and jump off.
Thanks, Brandon. As part of our design,
And if you're into more cold experiences, you can just go over to our cold mountain, where the heat exchanger is turned off. Actually, environmental.
Shed pet.
Yeah, I mean it's a big shed. It's a big shed, so it's fine.